Okay, so what I want to do is talk about regression. Up until now, we've talked about how certain variables behave, but only in and to themselves. So things like the muzzle velocity of a rifle, or um, the height of people in a class, or the strength of a piece of material. These are single variables in what we call univariate data analysis, and so dealing with one variable. What's sometimes a lot more interesting is to deal with more than one variable. And so we want to see how two variables relate to each other. So we're going to have one variable that we're going to change, and then we're going to watch its effect, or the relationship that it has with some other variable that we measure. So we're going to measure both variables and plot them. And so this is a really powerful tool for determining and examining relationships between variables. Now, just as an example, I'm starting with this simulator. I'll put a link in the description of the video. This is a pendulum simulator, and so what we are simulating here is that this is a Java application, and it's simulating the swing of a pendulum. And if you at all look into the physics behind it, you'll see that with a small angle approximation, which is good in this case out to about 20 degrees, where we can approximate a small angle by saying that sine of theta is roughly equal to theta, in radians, of course, we can see that the period of the pendulum swing, or the frequency in like fashion, is actually independent of the angle that it swings at. That's why it's useful for things like clocks, etc. Because even if two swings are different, they have the same period of time for a small angle. So what we are going to do is I'm going to come down here and click on other tools, and that gives me a little stopwatch. Okay, and what I want to do is I want to time the period of the swing, and then I'm going to vary the length of the pendulum. So there should be a dependence on it physically of the period on the length of the pendulum, and it should change. So I want to explore that relationship and see what it does. So what I'm going to do is I'm going to use this stopwatch and to average out the error in my timing. So this introduces some human error, which is going to be hopefully nicely randomized, etc., and we should get a normal distribution of data, or normal distribution of variation of the data. What I'm going to do is I'm going to time not one oscillation but 10, and then divide the result by 10. So you can see here I'm going to measure the period for 10 swings. So the period would be, for example, starting here on the right, tick, tock. That's one period. So, one full wave cycle. I'm going to measure 10 and then divide the period for 10 by 10 to get a single period, and that divides my human error by 10. And so that's one way to kind of mitigate some of the error that would introduce. And so what I'm going to do is I'm just going to pick one side and say start 3, 4, and we'll go to 10, 6, 7, 8, 9, and 10. And so stop, and then I would put that data in here. I would say for a length of 0.50 meters, I could do 12.67 seconds for 10 swings, which means the period for one would be 1.267 seconds. And so what I'll do, I'm going to go ahead and do this data and increase the length, measure it again, and I'm going to fill out this data table from 0.5 meters to 2.5 meters, and then we'll come back. So now we've got our data. I went through and did all of these trials, and just went ahead and redid the first point. And I want to look at the relationship between length and period. And so I can select those by selecting the top of the row, hitting Control, select the two rows, and plotting them like so would plot whichever column is on the left in Excel, by convention in Excel. Whatever column's on the left is X, and whatever's on the right as Y. Given that I set the length, this is what we would call the independent variable. I set this and then measure what happens to the other variable, the dependent variable. That's what I want. So usually I'll put my X variable on the left just so that's nice and easy. So I'm going to go to the Insert tab, then give myself a little scatter plot, and we've got some good looking data here. Now, unfortunately, Excel does a pretty poor job of making professional looking graphs. So we'll notice a few things right off the bat that I tend to like to correct. Number one, and I don't know why it keeps doing that. Number one, we very rarely actually use a title like this when we're going to put this in something like a technical paper, or a journal publication or a thesis or etc., we don't use a title like this. So first thing I do is get rid of that. Number two, we're plotting one thing here. The legend really doesn't tell me anything at all. So I'm going to go ahead and get rid of that too. And we also notice that even though we put labels on our columns, Excel doesn't seem to be smart enough to pick up on that. So what I'm going to do is insert, or I'm sorry, you go to the chart tools and layout, and then if I want to add axis titles, and by the way, you must add axis titles. A little aside here, when you make a plot, when you're putting it in a journal publication or a technical paper or even just a report, a memo, etc., you want that graphic to be able to stand on its own. If you're like me, when you pick up a piece of literary work, you're going to flip through it and look for pictures. Why? Because I don't know, maybe I'm ADD. But you're going to flip through it and look through the pictures and hopefully glean as much information out of those pictures as you can. And then if it seems interesting, then you'll go back and read about the pictures. But what's really important is that graphs and tables stand on their own, that they need no extra description in order to explain what you're looking at. And so we need to be explicit with our titles, and if we need a legend to differentiate between types of points and lines, etc., then we need to put that legend in there. And then you can put the extra information, a description, a very concise description of the graph in the caption in whatever you're writing. But to start with, we need titles, and we must absolutely have units. And so I'm going to type pendulum length here, and that was in meters. And then I'm going to add a vertical axis title, and we generally use a rotated vertical axis title. Just it looks a lot more professional than anything else. I'm not sure why they put the others in there, but then the dependent variable was period and seconds. And notice I said pendulum length. If I just said length and period, you wouldn't be quite sure what I'm looking at. Because I said pendulum length and period, you can get an idea. Okay, yeah, I'm looking at, they varied the length of a pendulum and then measured the output period, and that's what I'm looking at. So here we've got our data, and it looks very linear. It's very good looking. One other beef actually that I have with this, they always put horizontal lines, they never put vertical lines, and the horizontal lines are kind of a little bit what I'd call severe. So to make those lines a little bit more visually pleasing, I'll go to line style, and then I give it a center line type, because you can see that's a lot less busy to the eye. And I want to go ahead and add vertical grid lines, because the whole point of grid lines is to allow you to draw some, to give you some scaling inside the graph, so you don't just have this big white background. So when appropriate, in other words, where you think that might be useful, it's worth it to go ahead and put those in, but try and make sure that they don't dominate the graph. You don't want to make the graph too busy looking. This is okay because the grid lines are muted, and it makes sense. So I can see, okay, yeah, I started off at 0.5, ended at 2.5, and I have a pretty regular distribution, for example, in the y, because of a pretty regular distribution in the x. So we look at this and we see, hey, that looks a lot like a line. So the question is, what do I do? How do I glean information from this? And there are two ways that we generally, just even inherently by looking at a graph, will glean information. You're doing either interpolation or extrapolation. So interpolation is when we look between points and say, well, I could basically guess at what the relationship is from here to here simply by approximating these points with a curve. And interpolation gives us an ability to then, instead of explicitly reading the data points and saying, well, if I want to know what the period of that pendulum is at 0.67 meters, then I need to go measure that value. Well, actually, if we draw a curve, we could interpolate and say, well, I know what the value is at 0.6 meters and what the value is at 0.7 meters, and I could use a best fit curve or something to then put in any value for the length in between 0.5 and 2.5 and get out a period that should be, should be valid according to the relationship. The problem with that is, if I just fit any old curve to this data, I can't extrapolate. I can't go outside the bounds of my data. So let's take a look at that. I'm going to right click on the data series and click add trend line. And for right now, let's just display the equation on the chart, display the R-squared value on the chart. We see an R-squared value of 0.988, and this is a very often misinterpreted value. People generally will think that an R-squared value close to 1 implies that pendulum length significantly affects period. And that's not so. We need to get through our minds the mantra that correlation is not causation. This could just as easily be a graph of shark attacks and ice cream sales. And so we need to be cognizant that this is not implying that one causes the other. Correlation, again, is not causation. But it does say that there is a relationship here that is closely matched, as far as we can tell by the data we've got, to this line. In other words, this line, there's a closeness of data to this line, and the relative closeness of data, if it were perfect, if the line hit every data point, R-squared would be 1. What R-squared, the way that we generally treat it as engineers, what R-squared is telling us is actually that the distribution of points about whatever curve you're dealing with, whether it's a line, or I could go back and change that to an exponential, and I still get an R-squared value. What the R-squared value tells us is the distribution of the points, how far they're spread from the predicted value by the curve. And it compares that value, what we'll call sigma yx, to the overall dispersion of points in y. And so we can see whether this is a close fit relatively in terms of the spread of our data set overall. So we look through this and we see, okay, exponential gives an R-squared at 0.959, so 95%, 98%, logarithmic about 98. Polynomial. Now, polynomial is powerful. Watch this, 9967. That's pretty darn good. And I can actually approximate, if I do a really high order polynomial, I can get a really good R-squared value. The question is, why would I do that? Is that significant? And what we find is, if I actually know the relationship between pendulum length and period, do I select the function that gives me the best R-squared value, or do I select the function that matches the type of function that I want to use? We get a very linear function, but when we go back to what we were talking about, extrapolation, this curve doesn't tell me anything. This line doesn't tell me anything about what the data might do past the ends of what I measured. Because it doesn't actually have any physical significance, these values aren't physically significant in any way. They're simply a best fit line coefficient. I can't get information outside of my curve with that. If, however, I derive a relationship from first principles between pendulum length and period, which we'll do, well, I'm not going to derive it. We'll just look at it and say, oh, hey, by the way, we know this relationship. We've solved this differential equation. Because of that, we could find an equation of the correct form and then use it to describe the data outside of where we actually took measurements. That's more useful. I went ahead and brought the data over into SciDavis. Again, you can go download this program for free. It's on the ME288 website has a link, or you can go to Google and just search for SCIDAVIS. This is an analog for QTIplot, a Linux program, and then alternatively, the commercial package that is very similar to this is called Origin, but it's a bit too expensive for most students. So we'll stick to this. This is indeed a very powerful program. So you can cut and paste cells directly from Excel, and what I'm going to do is select these two, and you can just hit Control to select the two columns like you would in Excel, and then go to Plot and hit Scatter Plot. And we see the same plot that we got before. It looks very nice. Again, we get this title that we don't need. We get this table that we don't need. I'm going to revise my axis titles to be accurate so I can be reminded at what the devil I'm looking at. And this is pendulum length in meters. And then the y-axis is period in seconds. So I don't like the scaling. Let's go ahead and set that from 0 to 3.5 so I can see where 0 is at. And again, we get basically the same thing. And if we go to analysis, we can do the same kind of fits that we could do in Excel. So if I want to fit a linear or fit a polynomial or exponential growth, decay, etc., these ones are built in. And we find we get 0.988, about the same R-squared value that we got before, and similar regression values. Now, it won't directly print it on the graph without you actually doing it, which is fine, but if you need to read the values that you're getting for your curve inside Davis, what it's actually giving you is the raw output from the solver that it used to do this solution. So it's saying you've got a linear regression fit of the data set, and so the function is a times x plus b, and a and b are the parameters that it's solving for, where x is the x variable, and then the output is going to be according to the y variable. So we find that a is 0.852, b is 1.119, and they actually even go on to give you the error terms. A chi-squared measurement, which talks about goodness of fit, it's a different measure of goodness of fit, and then the R-squared value, which is really what we're going to be more concerned with. But we see again, hooray, we've got this line that actually is meaningless. And so I'm going to double click on that line, go to the linear fit, and delete it because it's really not useful for much. So what we said was, we know that the form, we know the form of, what we said was we actually know the form of the function the way it ought to be physically. And so what we want to do is let's go apply that. And so if I go to the fit wizard, I can put in here any function that I want. And so we know that t is equal to 2 times pi, 3.1416, close enough, times the square root of L over G. Now, a couple of caveats here. T, as far as this program is concerned, is y, and it is equating y to whatever's in this box, so I don't need to put this here. Okay, it's assuming t, or our output in this case, is going to be equal to whatever goes in this box, so you don't need to put the t equals in there. L is, in this case, x. It's our x variable. And I want to solve for g. So we always need to use this to solve for some parameter. Otherwise, what's the point of applying the fit? So let's use this. We can use the pendulum length and period of oscillation to approximate a value for the pull of gravity, wherever this simulation was purported to be. So if we do that, come down here and click on fit, and then this is just an option to give you the ability to change the starting value. So if you need to guess a value that's closer to the actual value, sometimes it won't converge if you don't, then you can do that here. But really all you need to do is hit fit and then fit. And instantly, boom, 6 iterations, status, success. We get an R-squared value, look at that, of much better, 0.996. It's very, very close. And what does it find G equal to be? 9.84. That's very close to 9.81 in the United States anyway, as Dr. Pasek would say. So we find a value of G that's pretty close. And there's a difference in it because our data is imperfect. We have some error, and we fit the curve to the data. Now, what if we just said, well, okay, I want to compare this data to the actual function that uses a good value for G. I just want to see whether the data is varying from that function. Sometimes that's a useful skill. And so let's do that back in Excel. If I come back to Excel, I can very easily say, well, I know that the period should be 2 times pi, 3.141596, or 3.1415, close enough, times the square root of L over G. And let's say I know that G is 9.807 meters per second squared. And then I can fill that column down and then plot that with it. Now, people would say, well, how do I get the R-squared value? So I've got this curve, and let's go ahead and add a function. So we're going to add, we're going to select the data, we're going to add a data series where the x values are the length, the y values are the predicted period, and I'm going to change the way that that gets plotted to a line, because that's not, that really should just be a solid line with no marker. So the red line there is as predicted by the theoretical function, and then the data is distributed around it accordingly. The question is, okay, well, we were able to get an R-squared value inside Davis. Can I do that just manually here in Excel? So again, I'm going to label this theoretical period, and that is again in seconds. We always want to include units just to be consistent here. Now, we know by definition, if you look into the literature, if you look at the MA288 website, we have some information on R-squared. So we know that R-squared, and I'm just going to type this for reference so you can see it, R-squared should be equal to 1 minus sigma yx over sigma y, quantity squared. So the sigma yx over sigma y is squared. What is sigma yx and sigma y? Well, we mentioned this before. Sigma y is simply the standard deviation of the y data. So here is my sigma y. I'm going to shrink this graph a little bit and get it out of the way because we're going to do some math here. So here's the graph. Sigma y is simply the standard deviation of the y. So I can say that this is equals to the standard deviation of C to C, and I get 0.53. Now, the question is, what is the comparison between the variation of the data about the prediction? So let's say we have an error term, and the error will be in seconds in this case. So as we're reading this, what you need to realize is x is set. It is the independent variable. I'm going to measure the vertical error about the predicted line according to the data that I have. So the error would be simply the period minus the theoretical period. If it's greater, then it's going to be positive. If it's not greater, it's going to be negative. And so I can just do that error, and then I'm going to find the standard deviation of this error is sigma y given x. So for a given x, the distribution of y about the predicted line is equal to the standard deviation of this error term. Now when I do that, I can say, well, what is 1 minus this sigma yx over sigma y quantity squared? 0.996. And so we can calculate what the R-squared value is, and now because we have a significant function here and we can verify it with data, if this was a spring and I was solving for the spring constant, I could use the algorithm inside Davis over here. Say this was a spring curve, I could apply a linear fit or whatever kind of spring it is, apply that fit and use this technique to calculate a constant of that item, whether that's, you know, the strength of the aluminum, or whether that's a spring constant, or whether that's a damping constant or damping ratio or whatever. I can actually do that by applying these curve fits and backing the values out with the regression. So regression is a very valuable tool for doing tests on things that we need to either verify, so I could find the R-squared, the difference between a theoretical curve with the published number, and see if that matches what I see. Or I can do it the other way and say, well, I don't know what this is, so I'm going to measure it and estimate it. Either way, we can see the closeness of fit with the R-squared value, and we can thus, if this is based in theory, extrapolate. And so now I know, you know, if this was Hooke's law, I could say, well, as long as the spring is linear, I can assume that this behavior would continue outside the bounds of where the data is, which is a very useful statement indeed.